So we're trying something different today because I never am prepared these days. We have a warm-up band, Selim doing actual slide presentation, and then I will be just talking with the paper. We'll see how that goes. Okay.
Yeah.
So Selim first, and it's different from the announced topic, but it's still useful.
Yeah, we hope so. Yeah, I'll be explaining the topic of my current work, Causal Structure Inference in Time Series at 3 different levels, kindergarten, high school, and grad. Starting with kindergarten. So the example I'm going to give at kindergarten is going to be a simple game that I call walk, tap, hop, where the rule is the first player has to walk for 1 second, then tap the next player, and the next player hops, and the next player does the same thing, and so on. So the golden rule is 1 second walking, then tapping, then hopping. So now the rules are established. Then I'm going to ask the kids, now let's imagine what would happen if we went to the park, to the playground, and we could only see 2 of our friends. We are seeing the first friend and the third friend, but maybe the weather is foggy or there's some obstacle in the way that makes us unable to see the second friend. So just by knowing the rules of the game and seeing the first and third friend, are we able to infer that there must be someone else in between? The answer would be yes. Are we going to know who it is? The answer is no. So in our head, it's going to be, okay, someone, but we don't know who. So maybe we will imagine it like this, like a placeholder player. Yeah. So this would be the simple causal chain in the actual.
But you can have 2 players, placeholder players, or you have infinite number of placeholder players in between, right?
Yeah. How do we know that there's only one placeholder player? Because we are measuring the time. So we are going to say walk 1, walk 2. So it took 2 time units. But we know the rule is every connection is going to be just 1 time unit. So there has to be 1 player in between. In the graph, this is going to be like 3 nodes. We observe the beginning node and the end node, and we will say, okay, there must be another node in between. But do we know what that node is? No. So we just put a placeholder in. So that's the way to infer the causal chain at the kindergarten level. I'm not going to explain all the cycles and bidirected edges, anything like that. I think this is going to be a good stepping point for the kindergartners because I think the rest will
be already off playing.
Yeah, they are already off playing. Yeah, they learned the game.
Yeah.
So next is high school level. For high school level, I thought they probably don't know what a time series is, but if we explain to them, they can understand. So here we would say, like, you have some variables that you measure that you represent as nodes, and you measure them at every time point. So each row, like the first row, is for variable A, node A, and node B, node C, until infinite or however long you are measuring it. But what about causality in time series? So we use the time series that we just learned, and whenever we know that one node causes another node to do something, we include an arrow. So if we know that A points to B, when an action in A causes an action in B, we put an arrow in between them. And we do it from time t for A to time t plus 1 for B, because we know it's the same rule as the game for the kindergartners. We know that it has to have 1 unit lag of time. It has to take 1 unit lag of time. So that's the causal error. And if necessary, we can explain, like, again, bidirected edges or whatever else. But I think from this, going to the compact representation of the unrolled time series graph would make sense. So instead of the previous one where we had rows for each node, here we will just say, hey, A points to B, and it takes 1 time unit, so we can just do this, and the same thing for B to C. So it's that simple. And I want to give them a concrete example from real life, the vending machine. We will say, okay, if we are the designer of the vending machine, we know what happens in every step of the process of getting a snack when you go to the vending machine. So it's like you press the button, something happens, and the item drops. But if we are just the user, what we see is only the 2 steps. Just press the button, we don't know what's going on, the item drops. And from just this observation and the knowledge of how the game works, that it has to be all unit lags, every direction, every causal error, we will say, okay, there has to be something. I'm also assuming we know that it took 2 time points between the button press and the retrieval of the snack. So by knowing the rule, we will say, okay, something has to happen in between, but we don't know what. If we didn't design the machine, if we didn't have the true graph, true causal graph, we wouldn't know what this node is. But by knowing the rule, we would know there has to be something. What is it? We don't know, but there has to be something. So that's the kind of thing, the simplest chain that we are trying to infer in causal graphs, causal time series graphs. And then we move on to the graduate level with the introduction figure that we had. Now, this is the kind of figure that I think grad level students would understand and like, because you have everything explained very clearly. On the top, we have the unrolled graphs. On the bottom, we have the compressed versions. Like on the top left, it's everything in every time point. And then in the next step, we are only left with what we observe. And based on what we observe and the rule that every...
You can point with your mouse. Where should I?
Here. If we are just able to observe this, and we know the rule that every connection has to be 1 time unit long, then we will say, I see that node 3 points to node 5, but it takes 2 time units. This is impossible. There has to be something in between. Then we are also seeing that node 3 points to node 5 at 3 long leg as well. So there is the leg set that's introduced here, 2, 3, 4, until infinity. This would mean there is actually a node between 3 and 5, and that node will have a cycle on top of it, a self-edge. And we introduced that node in our causal graph here as R2. So all the path lengths that are possible to travel from 3 to 5 are first 1, 2, then by using the self-edge once, 2, 3, and then using it twice, etc. We can do this kind of thing for all the leg sets, and we put this into a constraint solver so that we don't only consider the lag sets individually, but we consider them together and sometimes come up with a more compact reconstruction than the true graph, like in this example.
Yeah, so one comment is we have the maximum correlation is not causation. But here, the problem is that even when it is causation, what you're seeing is not what is actually happening. So, and it's the middle graph is sort of actual observed causation.
Yeah.
You can intervene on the variables and you can approve those lags and edges that, okay, if I intervene on 3, then 5 will feel it. And if I intervene on 5, then 3 will not feel it and the same lag. I mean, it will eventually feel it though. So like you can all test that, and yet it will be not the right graph or not the base graph that's generated. That's kind of the important message. And as Mike said, math ignores a lot of reality necessarily. It is a lot of reality is ignored too as well. Like we operate with infinite lag sets and things like that, although there will be loss of information with time, but we are just ignoring that, right? It's mathematical for now. Like assuming when there is a path, it's detectable because those sets in the middle graph, the sets of edges, right, are like sets. The set weights, the weights of the edges, right? They are we pretend that they're measurable because you have to take them from somewhere. So we pretend that you can measure them from data. And you can to some extent. Like all of them, but the infinite ones are probably measurable, but infinite will die out sometime soon, before infinity.
To deal with infinity, you will have to include a cap in your actual implementation, of course.
No, not even that. Even when we do that, we're still in the realm of mathematics that calls itself computer science. But like in reality, with real data, it's going to be messier, even messier. We can model, but make other assumptions of how fast they are not measured and things like that. But those are assumptions.
And related to this, I know a good concrete example that could be related to our center is the relationship between the occipital cortex and parietal cortex and temporal cortex. Now, usually from the occipital cortex, a bolt signal can be measured that causes an action in the parietal cortex and the temporal cortex. And maybe in your measurement, you won't be able to observe what's happening in occipital cortex, but if you only observe parietal and temporal, you can infer that there must be a common cause, and you can then, in your inference result, put in a placeholder as the common cause without saying, hey, this is the occipital cortex, if you don't know any domain knowledge or anything else. So this is one example that could be happening soon. I think people have done things like this, but maybe not exactly in the way we are doing.
Well, but also the important part is Jordan's favorite, gut bacteria, and that is never measured, heartbeat and breathing and all of that. They do affect everything or something or etc., and we don't include that ever, right? But they're there, so it would be good to know what else is there. That's like, if we measure the lags, that we can say, well, there's something else there that affects the brain, or there is nothing else. That would be good to know.
That brings us to the area of informed causal inference. Maybe you will provide some sort of domain information to your solver. Like you will say, hey, occipital cortex has this feature, and that's the only thing we know about occipital cortex. And we have observations from parietal cortex and temporal cortex. Give me your estimation of the likelihood of the common cause actually being occipital cortex. Maybe if you do it right, you are going to say, hey, with 99% confidence, I can say the common cause of these two comes from occipital cortex. Yeah.
I'm just thinking about 15 minutes.
Yeah, okay. Thank you. And that's
okay,
what
I
I
can do
said.
this. Okay, I hope it prepared you for what's coming, even though the topic is unrelated. But thanks, Selim. Oops, where is the? Oh, I'm unable to share. Okay, the way it's shared is different. Here we're sharing the screen. We see my notes. Yes, we do see my notes. And so yeah, apologies. I was supposed to present, and second time in a row I'm not prepared, but I thought bailing out is just bad taste. So the Titans, learning to memorize at test time. The theme for this semester for me was to think about and make actually a course, which is for next month on my list, about systems that deal with dynamics, feedbacks, and things like that. So memory is one of them, one of those systems, because it helps you to deal with time. And this paper came up as...
You may want to zoom in on the Mac itself.
No, I need to zoom in here, but
You can zoom in on the Mac, I mean.
but then the page doesn't fit.
You don't have to fit the whole page.
I cannot zoom in on the Mac.
That's insane. What?
Yeah,
How about
yeah.
command plus?
No, it's a different thing.
Use this app before. It's not suck that much. I've used the Remarkable app before. It did not suck this much.
No, it's great. I mean, what's the problem?
I can't read any of the words on it.
Oh, you're not supposed to yet. Okay, there is a thing I need. I think I may be able to. I think I may be able. I turned off the rotation. I need to make to be able to rotate. PDF settings, increase, enable. Mike, what are you doing? Delaying this wonderful presentation. I was so prepared. Share. No, I cannot rotate for now, and I turned off
It's okay, I'll just develop supervision.
the automatic rotation. Yes, for this. Well, the important part you need to see is this Google research, right? Trust me, I work for Google research.
This is not from cranks at some crazy universities.
Yeah, and I guess, well, okay, anyways. And I will be writing here. And I will need the white space a little bit. But let's talk about learning, memory, loops, and things like that. So first about learning, right? We have a system with some parameters, and we want to tweak those parameters somehow. So we came up with a system that there is a data point and there is an output label produced by the system, and we're training the system in a loop, well, in a different loop. We're training the system in a loop by adjusting those theta parameters. And so there's dynamics going on, and the dynamics that going on is involving and I'm improvising, so I've heard people online say, oh, you should come prepared or not prepared. This. So we're doing gradient descent with respect to loss, and then we're creating the entire field that is misguided because it says, well, the model that we release, this F, is learning. It's AI and everything, but there's no learning after we are done here. We're done training. This is the dynamics, the actual learning, what we think about learning. Learning as the process of change, of adaptation, happens offline, and then our model just runs, right? And then another thing that we gave up, and I will not give you visual feedback, but another thing was memory and state. Recurrent neural networks kind of address the memory and state problem. They introduced a state that was carried through the time independently of parameter values. So it's a state that is carried through the time, adapted according to input at every time step. And there was a lot of work done there. And then transformers came, and before transformers came, neural networks, recurrent neural networks, introduced the thing attention, which was a misnomer, but I mean, it got stuck. Introduced memory, that of a high order memory, which we called attention. Before, the memory was carried in that single vector that is adopted, that is changed, adapted on the fly, every data point, even without data point, it can be modified on the fly. There is no learning happening per se in the gradient descent business. There is no gradient descent, but the learning functions, the functions now that take inputs, take current state of the model and decide if the current state of the model, which is memory, that vector here, needs to be tweaked. So, but then people, when working on sequence-to-sequence models, you have a long sequence here, and you produce an output for Mike, memory output as a vector. And then another sequence starts initiated from that vector, and this sequence is reading in a long sequence. And this reading is, this sequence produces a long sequence. And there is tiny bottleneck between them, that memory that was stored. That's how attention was born. Attention was born, well, we have all states of our memories through time. Let's attend to any of them that are more useful for at this point of time. Any or all are useful for this point of time, are they useful for this point of time. But this should have should sound to you already like, oh, but this is just a memory with a corpus. You have a corpus of your states at, across the time, and you're looking up. Like, okay, wait, well, I need to say something here at this point. Let me look back and see what from the past, but we called it attention because in order to retrieve memory, you're paying attention to subsets of parts. So recurrent neural networks, internal state, etc., etc. Transformers, forget the sequence. Everything will be packed in one pass, so the sequence goes together into the, and I will not explain transformers, but it's important. Everything goes together as an input, and each input is related to each other input, self-attention, because you have this correspondence of each sequence element to each other sequence element, you get quadratic complexity. Because of that quadratic complexity, despite that some people claim it's logarithmic, you are stuck with limitation in how long your memory or context, we call it right now, it's just the input to the transformer system can be, right? So when you're stuck with that, there is a linear transformer people have tried. I'm trying to get my mouse to the other screen to read my notes. Not those notes. Oh, interesting. Give me one moment. Okay, so what happened with transformers? In order to,
It's not on the screen.
I'm not showing.
Okay.
In order to, this is just for me. In order to bypass the limitations of transformers, is that when you're increasing the sequence length, your context or your memory, right? Not your memory that you're operating with, but the corpus that you're looking at, what we call context, prompt, or whatever. You need to quadratically increase the computation and memory requirements on the model. People thought about various solutions, including state space models that are claimed compatible, but let's assume it's a failed attempt at this time. And other various failed attempts to generalize the single shot nature, let's ignore at the regressive generation for now, of transformers, and make an RNN out of transformers. So combine the idea of recurrent neural networks when you transfer memory from one window to another window with transformers. So that's what the paper on the surface is about. They spend a lot of time misleading me, explaining stuff that was already done by other people. For example, memory as context, right? Memory as context has been done in many transformers. And let me see if I have a good, the good old Claude is probably better for that. So memory as context, memorizing transformers, transformer XL, block recurrent transformers. Memory as context is when you take your previous state, store it somehow, and pass it as an input, partial input, part of the prompt to the next state. So your transformer is scanning now. It is scanning either as a sliding window or as a stepping through window. Instead of working on the entire sequence, it works in a small quadratic model that is fixed. So the sequence gets longer and longer, but your memory is fixed. It doesn't get, it's not blowing. Memory and computation is still affected by the sequence length. So other transformers. Didn't work. All of those attempts are failed so far. So what is actually used under the hood is different. But anyways, and then memory as what is it? Memory as layer, memory as gating. When your previous RNNs use it more or less like that, but when your previous memory is used to gate your current state. So you compute the gating function and you decide which part of your current context are important. So and then you pass an update. So all of that has been explored, and paper unfortunately spends a lot of time on that part. But that part, when I was reading it, is not helpful because, well, it's been all tried and done, like this persistent memory and how to incorporate memory and things like that. So for example, you have a memory module. This is your Titans now. We're jumping inside of the paper. And you have this memory module, and it works on a window of context. Your entire sequence is split into windows of context, and this is your ST. And you had a previous context, ST minus one previous context. So this is large enough, I don't know, 200,000 tokens. You don't want to go larger. It's 200,000 tokens probably you can run on your laptop. But stitch together 200,000 tokens, you quickly be on millions. And we can handle that by having a model that takes your queries and produces the hidden state. This model now contains memory about the previous window. I can't write there, the previous window. So whatever it outputs is a sequence, you prepend it to your actual sequence, to your prompt, or post-pend it, they change it from one paper to another. It doesn't actually matter. Yeah, it doesn't matter. It's just additional information that it's what matters. What the heck? Screen share, lost connection. GSU Wi-Fi is unstable. Let me do it again. So the main point here is that this memory thingy is an MLP in this case, multi-layer perceptron, two-layer and so on. It doesn't matter. It takes vectors which are projection of your current sequence query and decides what will be the hidden states that will be passed as additional input to the prompt to at this stage, at this model. And this prompt is passed through a transformer model. Then they have those tokens that are learned during training. So the story, a bunch of the paper is spent on analogies with memory system and the brain, long-term, short-term, working memory. And so what they call here is we have short-term memory is our context. Like here you have everything. So this is short-term memory, if by analogy, short-term. This is working memory. Working memory, and this is long-term, say. So long-term memory is learned once and for all. Those are fixed tokens that are learned during training, and they sort of characterize the distribution of the training distribution. That's what will be learned. It's like we learn tokenization on the fly, something like that. But tokenization, at least, is a little bit dynamic. Those are just learned tokens, and this is working memory tokens. They are produced from current context by the memory model based on the current tokens, based on the memory model's parameters. And that's the key. And then you apply attention to the new sequence. So you pass it through normal processing, basically. And then this new sequence, and here where they lose me, but what I will explain right now from this point is my understanding of the paper. it's not what actually is written there because I have no idea what they actually do. The reviewers complained as well, and like, yeah, I didn't have time to go through the code, but
The share button is covering the math. The share button is covering the math on the projector.
oh, there is no math there, but okay.
There's a little bit of math. I see a tensor.
Oh, it's no, it's not tensor product. It's just element wise. It's gating. That's how they decided to denote it.
Symbols mean things.
Yes, exactly. They don't hide. Not in this case.
I don't
Yeah.
even know what the double bar thing is. Is that?
It's concatenation.
Oh my god!
It is. Yeah. We recorded. So this is concatenation. So you're concatenating three sequences. This thing is concatenation. And this is just element-wise. This is gating, right? Engineering notation is mixed with mathematical notation. In mathematical notation, Adamart product is just that element-wise. In engineering notation, it's a valve. So that's why it is displayed as a Kronecker product, which is not.
I see.
Which is not. So we take our output is just gated by. Ooh. I don't know what the star notation is. My apologies. Yeah, so it's very hard. The paper is written in this very, very strange way. But what I'm doing now is also very strange. I'm explaining you details which don't matter. But like, so you can understand what I was talking about, memory as sequence or memory as context. You have, again, one more time. You have windows of context. This is a sequence, your text. They're specifically working with transformers and with text only, as if that's everything. But S sub t, S sub t minus 1, S sub t minus 2. So you process one thing at a time. Your complexity is contained. It's not growing indefinitely. Then you need somehow to pass information to the next window about the past. And it shouldn't be just about immediate past, even though it feels Markov, it's not necessarily Markov. Like RNNs, when you draw them, they look Markov, but they're not Markov because the memory that you're transferring is modified in a way that it contains the entire past history. Can, potentially. Or the history can be wiped, Yeah, like this is the bad part. Let me try one quick weird thing. If it works, then we all are saved. Extra bright, no. Lock rotation. I did lock rotation, but what if I don't lock rotation? What happens there?
Beautiful. There we go.
Okay, a little better.
Now we can see things. I don't understand why they bring up persistent memory. It doesn't make any sense to me. That's just how all transformers work.
We're recording. So, okay, anyways, this is one possibility. Well, the key here. In RNN, what we are transferring, this is the key, and there is an important, interesting part, which was harder to grasp. What we're transferring in RNN is a vector of data that we're modifying on the fly. And the function that modifies this vector on the fly is learned during training. What we're doing here in Titans, we are modifying the function. And again, disclaimer, this is what I understand. I was trying to make the paper cool, and this is the best, most interesting way for this paper to be read, because otherwise it's just, an exploration of what has been already done. And I'm 99% sure that I'm correct. This M function, as you see, it's modified here. M is an MLP, a multi-layer perceptron. Could be any other neural network. Just for simplicity, they took multi-layer perceptron. So you are taking an MLP and you're modifying, this is your previous MLP. So the trick, memory as a notebook versus memory as a mechanism that is working, and you're changing that mechanism. You're like, oh, I need more gears, I need less gears, and things like that. So you're instead, before, when memory was a vector, this vector, before in all of the other work that I mentioned, that superficially on the surface or in the workflow diagram is exactly like each example in this paper. In this, like they're doing what has been already done with one important change, and I want to stress that because I will show how they do that in a second. This is an MLP. Before we were transferring activations, now we're transferring parameters. So it's the coolness of that, and back to our work with Reynal and everything. This is a second order function. So you're modifying the parameters and you're getting another function, which is now different. And then the function gets applied, et cetera, et cetera. When you have activations, then you don't apply them to anything. You apply something to those activations that are RNNs and whatever people have done before. Is that clear? Should I like try it from a different angle? Like the difference of self-attention is a linear function that is generated on the fly. It's a matrix that gets applied, but that matrix gets generated on the fly. So even though self-attention is like a matrix of activations, because those are the outputs that are multiplied, et cetera, but it acts as a function. Now they just like, well, we can do that to any function. It doesn't have to have this specific key and query form or anything. This is an MLP. So how does like the entire novelty? Sorry for doing that, but it's just so I don't know, so comforting. The entire novelty of this paper is here in this equal sign.
The scheduler for the updates.
No, the mechanism of how do they actually update.
We're saying the same words.
Okay, okay. I don't know this, like why would it be scheduled, but that's fine. That's fine. They have okay. Just for completeness, before we jump to actual core of the paper, we have 8 minutes. I promise we can do it. This is not the only way to pass information as context from previous to next. You can pass it as gate, which they. By the way, the most unhelpful figures. Sorry, whoever this like, I don't know what's on the figures. Some diagrams, but
the figures make sense to me.
They make no sense to me at all.
Maybe they're just like taking the MLP, slapping in the whole sequence, and then outputting this thing you append to store the attention.
Has nothing to do with the formulas. Formulas are much easier to understand, and there are 3 ways to do that. The figure doesn't describe that. This is completely misleading. What is that box of tensor? Oh, it's like my memory. It's a collection of books. No, not at all. It's a function, and it's an MLP. This doesn't represent an MLP to me. So let's skip. It's just like, why do you take the real estate of the paper with something that but.
We should also clarify that MLP is 1% of the big model's size proportionally.
Yeah. There is a model. MLP is just doing its thing. So you can just do this, right? You can only use memory when you produce the output, and you only use it as a gate. See, it's not present in the sequence. It's not passed through context. But this is kind of like ablation, because they already are doing that in the other way as well. And the third way, MLP as a layer, right here, you just modify, not MLP, memory as a layer, which is MLP in this case. But the trick, the takeaway point from this, and I don't want to look at the results, I'm not impressed on everything by the results, and they don't matter. The ideas are interesting. The results, I assume, are just saying, okay, it works. It's like they're not getting like stellar results or anything, but that's not the point. The interesting idea, the experiments, we don't have time for experiments. The interesting idea is that equal sign, and it's kind of presented in the beginning, but because of the way it is presented, and like this should be an appendix, like entire section with the figure and things like that.
That's a huge part of the paper. Like that's like make or break for the paper.
I mean, it's I don't know. I don't know.
If you don't have an answer to that portion, you do not have a transformer competitor. That's like the whole point of a transformer.
They're still, it's a recurrent model. They're still scanning the sequence, no matter what. So I'm already fine with that.
No, but like the difference from an RNN to the transformer is in the fact that no for
That you're not waiting for the previous input. Here you will be waiting for the
inference
previous.
time. Yes, you are. But for training time, the transformer deletes that, and so it makes it so much better to pre-train a transformer versus an RNN. If this model reintroduces that flaw from RNNs, where parallelizing of pre-training becomes very miserable, then you've deleted the main strong point of a transformer.
Well, so okay, what are they talking about in this section that you? But this is bad if I understood you correctly, that you can train only on neighboring windows in parallel transition, right? So you don't have long-term memory context then when you're training.
You don't necessarily need to do the entire unfolding sequentially at training time, at pre-train time.
Why?
That's the scary part. Because if that's the case, then
No, wait. Why? How do you avoid that?
for the transformer,
No, for the transformer it's fine. Here, when you have window and context.
that's what I'm saying. If they didn't have this section for how to parallelize their mechanism, this entire paper would be like not useful as a replacement for transformers.
Well, there are tons of transformers that already do that with a scanning window and things like that. And they engage into all of the possible mechanisms that are done here.
Like sliding window and like sparse.
I don't think they solve the problem that you're mentioning. Have you read this section?
This section I've only skipped.
I don't think they are solving the problem that you're mentioning. They're not training in parallel. And again, I can be wrong. They're not training in parallel on the entire, multi-billion length sequence. Quickly reading what's on the screen. So Mike's concern is that any kind of recurrence will force us to pass the gradients through the recurrence, back propagations through time, in essence, basically. And even though you have transformer at each of the block, but to get from the end to get to the beginning, you will have to do back propagations through time. Here, well, even with transformer, even with gradient availability at each time point, the gradient from future still have to get to this transformer that if it ignores the gradients from the future, then it only has the gradients about its current input, and the memory is not, the memory model is not
the memory model is not coherent if you train this naively like a transformer. I don't see why you can't train these decoupled though.
Well, because M needs to carry the information.
But you're training M at test time anyway. It's a tiny model.
I want to get to that. So, but then it's just train transformer. No, they are training during the training as well, and this is confusing.
Yeah.
This is confusing when the training of what is happening is not too clear at all.
Because I can see a version of this paper where they just reserve the spot in the front for the M module, and then you just. It has
to work during training as well. The transformers, the bigger transformer, has to be aware that this M will come, and for it to come, you have to bring it from the previous
bring it
context.
along from the beginning.
You cannot in parallel execute that. Mike raised the point that I haven't thought about, and I'm saying this talk is an entire hallucination of me of what this paper could have been. I'm not 100% sure what it actually is. But let me get to the coolest interpretation of what that paper is. So if we assume that this block is happening during inference, this block on the screen is happening during inference. It is not happening, it's disguised as if training is happening on the fly. We need like notebook LM or something like that with those questions. But if it's happening during training, then nothing, like it's just repeats, the entire paper just repeats what we have done before. But the point is that this happens during inference. We compute this loss, we take our current MLP that we have, and my problem is how do we start with that MLP then? So this initial start of the MLP must be obtained at the training. And we pass through the MLP the keys, which is just our data through the keys, right, past the linear transformation. And we minimize the loss with the values. And by minimizing this mean squared error loss, they call this measure of surprise. If there is no much difference between the keys and the values, then okay, the input is not surprising, or the projection is not surprising. So we minimize this loss during inference. During inference, we say, I'm opening up that equal sign. MT equals MT minus 1. How is that happening, right? And so it's happening through training of this loss via momentum training. This is just our momentum with an additional weight term, which they claim acts as weight decay mechanism, but which kind of, yes, because this capital M, curly braces, whatever, the M is just your weights. Regularly in momentum, those are your parameters. Your previous parameters plus the momentum term, which is accumulated as follows with the gradient, and you get your new parameters. And so what I'm unclear on, it's just one single step then. It's just like every recurrent step of your bigger model transformer, you update the model via a single gradient descent. And then what if you chose the learning rate incorrectly and things like that? So this model must be highly unstable.
There's another hyperparameter that we skipped over, by the way. If you grep for the word chunk, I found out how they do parallelization. They do recurrence within a small chunk, inside a small window. They split the whole sequence into multiple chunks, and they train the chunks in parallel. But within the chunks, it is recurrent. And so they kind of give up on the
You can do it with RNNs as well.
Yeah, effectively, yes.
It's called truncated backpropagations through time.
Yes.
They just don't want to call it because otherwise it's just too trivial, I guess. Or, well, I mean, I doubt they didn't realize it, right? It just sounds like backpropagation, truncated.
I think in truncated backpropagation, you still use this whole time series, but you use a window bit for backpropagation. And what you're saying is they're using chunks, and they train this chunk, and they use both the whole length of the chunk.
So the difficulty is that they're training two models separately, and the gradient dynamics of the two models are different.
Well, but those are different gradients.
Yes, they are. For the whole trend.
Well, this model is not trained. This model is only trained at inference.
It is trained at train time.
Well, then they what? They only train initialization of that model.
Yes, they train the initialization of that model.
Only initialization matters.
But the way that they reason about it is we split the sequence into chunks. The whole transformer sees the entire huge sequence, but locally within each chunk, you do the recurrent thing. And so the model, the big transformer, can learn how to work with the small model. But the big model has the whole gradient, whereas the small model only has the local gradient. And you treat the chunks as batches for the small model.
No, but those are different, again, those are unrelated gradients in a sense.
Yes.
Like the larger gradients don't flow through the smaller gradient, like they don't do second order gradients.
The dynamics are very strange.
Yes.
The scheduling is very
I don't know how they got it to work, and maybe that's why it's written the way it's written, because otherwise it would.
Well, that's my core concern with the paper. Why did they make the memory model so small? If you are taking seriously the idea that this is inspired by the human brain or like whatever other analog, you would make this like proportionally like double-digit percentages of the large models' size.
Oh, because then this thing is deadly on inference. How like it becomes too expensive to update
Is
and
it?
everything.
I mean, like,
Well, I mean, this is easy to compute. This is just one thing, but I mean, it doubles, triples the computation
it doubles, triples the computation.
of M
But it's a
relative to M size.
Also, I think maybe this size of them is actually comparable to activations, which it is being concatenated with. If you compare it with weights, yeah, it's small, but if you compare it with activations, it's comparable.
if you compare it to
The
activations,
D, but it doesn't
I don't
doesn't
think
matter.
that matters because the dynamics of that D, implicitly when you are trading a model that is a trillion parameters, you are saying that the true dimensionality of that D lives in that trillion parameter space. And so while the representation of the D itself is like 2,000 something, loading the dynamics of that in order to compress it correctly as memory.
Okay, I can guess, just to be devil's advocate or the paper advocate, is that a function is much more expressive than a static book
That I totally
you
agree
pass.
with. Yeah, that I totally
And
agree
so
with.
they may need much fewer number of parameters, way fewer number of parameters to transfer it in a functional form that does the work. Like it's applied here, it's applied here, right? It's applied here. So, and they are transferring the information through parameters. And then because function does additional work in those parameters, if only they did fixed point here, then it's like universal computation, but it's not, yeah. So then my argument kind of breaks down, but maybe that's the guessing. See, second order versus first order. First order is like you have to tell stuff. Second order is like I'm giving you a thing that will do the stuff for you. It's like you don't have to know much, and this thing doesn't have to know much. It's a deterministic mechanism. But here's my presentation. Overall, an interesting idea. Lots of spots that are unclear, absolutely unclear how they did this, that, like the stuff that we brought up. So it's very hard to reason about how good it is. And
it's also not clear how good it is in context of how big context sizes are for L.
Oh, no. Lots of problems. I don't like lots of problems with that. Let me try go to results, like we're over time. There are results. That's how I interpret those large tables without error bars. And okay, some results are there. Fine, they did experiments. Then this one is semi-interesting, which didn't make it to Nurip's paper, is the needle in a haystack retrieval of the long context. And this is a kind of weird experiment when you have long text and some keyword is, or something like minuscule is hidden in the context. Can the model find that word and retrieve in the context? And yeah, it's just, so they claiming, okay, our accuracy is still good with the sequence length. So what is it, million, right?
Yeah.
Okay. So, and even slightly more, 10 million, right? But with fine tuning, with no fine tuning.
Yes, we paid
50
years of science for graph.
Yeah, exactly. Well, okay, any questions, any discussions, any comments?
I feel like this is, I guess, kind of an experimental thing, but do you guys think this is comparable with RAG? Is it as good as RAG?
This is 100% better than RAG.
If it works.
I have very high certainty that something like this works already, and that the labs are doing something like this. You can tell too, if you're familiar with how prompt optimization works. The memory systems inside of ChatGPT and Claude have already surpassed something that looks like RAG. The way that transformers treat text context is noticeably different even as an end user compared to how they treat in-weight updates. And so even something like ChatGPT 100% is not just doing RAG. It's not just like building a text profile view and then retrieving that at runtime. There are like actual weight updates that are happening. And so maybe not this specifically, but maybe.
Oh, you mean LoRa kind of?
Yeah,
like
maybe
specifically for you?
Yeah, LoRa for me. And LoRa for you is such a useful form factor. It's bundled in with inference engines these days. Like VLM has an option for runtime LoRa, and LoRa sizes of up to.
Well, we're not running those models, so and only big models matter where you can notice that improvements and things like that.
What do you mean?
We're not training those models ourselves, right? Like we're not even running them locally. The big labs are running GPT-5.2, Claude, and
like,
whatever.
How do I say this? Does anyone here remember enterprise GPT-4 training?
Yeah, there was a thing like that. I don't
How
know.
do you guess that worked?
LoRa, yeah.
Yeah, exactly.
Yeah.
And there are many like smaller enterprise players that are doing exactly the same thing. It's such a cheaper way to do precisely that. It's like just train on all your exact user profile as a small weight diff, and setting that, it's like 2% extra on performance costs for practically memory without any of the complexity of this, and also without any.
All of this long rant is just to say memory in weights is better than memory in context.
Memory on context is very brittle, is the main issue.
I'm just trying to
Yeah.
understand what you said.
Yeah. RAG is especially brittle because you're putting so much trust in the embedding mechanism itself, and I don't actually believe that holds, especially for raw model embeddings.
When I need millisecond retrieval of my previous database, which I can tell you about the project I want to build when I'm done with the grand proposal, then only RAG can do it. Only those semantic databases or whatever, the Word2Vec lineage.
It depends on like what kind of memory you want. If you want.
Well, all I'm trying to say
Yeah.
is, and I was telling it to my son who's taking AP chemistry, is that when you get to a science that is not disguised engineering, then there is no single principle. There is a dinosaur era of a 5-year-old, tons and tons and tons and tons of things that you are free to choose from depending on what you're doing. And it's highly, highly problem dependent now. And you have infinite things. And like, for this thing, RAG is better. For this thing, whatever Mike is saying is better.
Yeah.
And like, you two have two different applications in mind. And so whatever his advice to you doesn't apply. Like, maybe RAG is better for something what you're thinking. Maybe stuff like that. But yes, it's creepy and so pleasant when it says, when I'm asking a from scratch question to Perplexity, and it says, this is the answer, but for you, I would recommend doing that. And I'm like, yes, you're right.
But how did you know that?
Well, I mean.
The creepier one these days is autocomplete inside of Claude Code. I've had Claude Code fill for me like a 3-sentence long prompt. That was like word for word exactly what I would say, and it was the strangest thing I've ever seen.
Oh, I want this, but I want this to work locally here. Well, sorry, online people, if you got here, that was a bad idea.
The crackpot section of the talk.
Yeah, we are done, and how do I? No, everything disappeared. All my controls. Keep talking though. Okay, I think I know what to do. And
No, but I just don't know why you care so much about local. Do you care about sovereign or do you care about local? Because those are two different things.
I care about sovereign, and I get it from locality. Sorry.
I mean, for me, it makes sense to have local stuff because we have sensitive data.
By online
then
people.
you actually care about